they start to diverge slightly, but not by much, a little bit, okay? So, yeah, so they're at low temperatures, they're almost exactly the same. It's kind of interesting. All right. So this actually, we don't really need to do a whole lot of difficult interpolation here. Let's see here. Air, for H1, air is at 20 degrees Celsius. What's that in Kelvin? 293. Do you need to interpolate these two suckers here? 293. Well, 290 gives you 290.16, and 295 gives you 295.17.
Probably 293.165.
Yeah. 293 point. I'm just going to go with 293.2. Okay, whatever. Okay, 293.2. Kilojoules per kilogram. You don't even need to do interpolation with that one. Okay. The enthalpy of air is only a function of its temperature, so that makes it pretty easy. Yeah, unlike water. Okay, the second one is 300 degrees Celsius, so what's that? 573. Okay, that's right between the two values. No, it's right on my thing here. It's right between two different values. Your book may be different, but mine, it's 570 gives me, what is this? 575.9, and 580 gives me 586.04. So where do you want to call 573? You want to add maybe yeah, 578 something maybe. I went with 578.6, but I wouldn't care if you differed by a little bit. All right? It's not going to matter. All right? Okay. So these are easy. Don't overthink these interpolations. They're simple. So the answer here, it's just plug and chug right now. Yeah, the answer here for the work, you do plug and chug. It's 578.6 minus 293.2. And then the question is, let me just write it down here. The work is equal to minus 285.4 kilojoules per kilogram. That's the answer to A. Why is it negative? Work going in, right? Yeah. You have to plug a compressor in the wall. Compressors don't work without plugging them in. Yeah. You have to plug it in. You have to put energy into the compressor, and the negative sign is all it's telling you is that that's work in. Basically, electrical work in, right? You gotta plug it in. Okay. So now, somebody asked in my morning section, well, if you ask for the power required, would it be negative? Well, if I asked for the power required, I wouldn't put it as negative. But I wouldn't. I understand there could be some confusion there. Okay. So, yeah. Okay. How do you do B here? The B part says, give it to me in kilowatts. So what do I got to do here? Well, I got to probably go back to this, right? Yeah, all I have to do is take that answer there before and multiply it by m dot, right? So how do I get the mass flow? Yeah, is that mass flow? 10 liters per second. What is that called? What's 10 liters per second? What would that be called? Volume flow, right? So, and this is the thing to remember. Some people in my morning section were like, I don't remember this, but I did this not that long ago, but it's okay if you forget. Is how do we convert liters to meters cubed? Yeah, it's like 1,000. Yeah, remember a meters cubed? Think about how big a meters cubed is. If I brought, let's say you said your fish tank was a meter cubed. I'd be like, oh, you got a big fish tank, okay? Because a meter cubed is pretty big, right? It'd be a little over 3 feet this way, 3 feet this way. I mean, it'd be a big thing of water. And in fact, a meter cubed of water is 1,000 kilograms, okay? and it's also 1,000 liters. Okay, so if you have 10 liters, you've got 0.01. You just divide it by 1,000. You've got 0.01 meters cubed, and that would be per second, right? That's what we call volume flow rate, or if we're fancy and we're in fluids, we call it volumetric flow rate, but it's the same thing, volume flow rate. So the mass flow rate, m dot, is equal to the volume flow rate, v dot, times the density. So how are we going to get the density? And don't tell me look it up in a table. How are we going to get the density? Yeah, ideal gas law, right? My morning section, they were jumping and saying, oh, go look it up in a table. Well, you go try to look up the density of air in a table. It doesn't work too well, okay? You have to use the ideal gas equation. So remember, recall the ideal gas equation. I'm going to have to write this a little bit below here. Recall the ideal gas equation says PV equals RT, right? So you can use that to solve for V. We've done this recently. V equals RT over P, right? Well, since the density is just 1 over the specific volume, right? Couldn't you also say the density is P over RT, right? It's just 1 over, reciprocal, right? So then, if I want to solve for the density, I've got to get the pressure. Now, the question is, well, what pressure do I use? What temperature do I use? Well, the only place you know where you have an inlet, where you know where your volume flow is at the inlet, okay? It says the air compresses 10 liters per second at the end, okay? So that's where you have to use your pressure and temperature, because that's where you know. I guarantee you, you're not getting 10 liters per second at the out. There's no such thing as conservation of volume, okay? You don't get the same volume in and out, okay? Definitely not with air, because air you can compress. You could have 10 liters per second coming in, and you might only have, 0.1 liters per second coming out, because it's compressed, okay? So you have to use the inlet, since that's all you have. So I'm going to use that. What is it? It's 120 kPa. Yeah, the temperature. Yes, definitely have to convert the temperature to Kelvin. Yes. 2.87. Remember that, the R for air. Don't memorize it, because it'll always be on your equation sheet, at least in metric units. I don't think I'll put it in. Maybe I will put it in English units. Okay. And then the temperature is 293, right? 293 K. And if you work this out and plug and chug and all that good stuff, you get 1.423 kilograms per meters cubed. Actually, I think you get 1.427. Sorry, I think it's a 7. Let's not get too hung up on that. I think I'm looking at my stuff. I think it's a 7. I'm sorry. Looking at my notes. Whatever. Not a big deal. Okay, so then you plug this all into that m dot formula. You got 0.01 meters cubed per second times your rho, your density, 1.427 kilograms per meters cubed. That's pretty simple, right? This is easy. 0.0143 or whatever, right? 0.143 kilograms per second. Right? And then if you get your W, if you work this out, I'll bring this to the other side, and you plug it all in, you get 4.07 kilowatts. That's your answer once you do all your plug-in and chug-in. By the way, for a compressor this size, that's probably a little low. We've probably made this a little bit too ideal. A real compressor probably uses a little more power than that, but not it's, I don't know. It's probably not too bad. It's I'd have to go look up some compressors and see what their ratings are and their power, but I don't know. Probably a little low. Probably use a little more power there. Compressors are loud. Good sized compressors, very loud, need a lot of power to do what they're doing, compressing air.
Would that be a negative?
Yeah. Again, it goes back to this whole confusion of what do we want to say? Is it negative or positive? Yeah, technically it'd be negative. I suppose I should keep it negative. Let's do that just to make everybody happy and keep it consistent. So hopefully you see turbines, compressors. It's just first law, get your information. Pretty easy stuff. Pretty easy. The last thing I want to look at is valves. Okay, that's even easier. Okay, a valve is really easy. Okay, when I talk about a valve, okay, typically in a diagram, like a thermodynamic diagram, I might represent it like this. Something like that. There's other symbols and things like that. You have flow in, you got flow out. And a valve is there to restrict the flow. Okay? And that's going to cause a pressure drop. That's going to cause a pressure drop in the fluid. Okay? It doesn't usually do too much else. When it comes to the first law of thermodynamics, though, it's very, very simple, okay? Because usually we model valves as no heat transfer. They're adiabatic. Valves don't do work. I've never seen a valve you had to plug in except if it had an automated, thing to change its, solenoid or whatever to change its opening. Besides that, I've never seen a plug in a valve. You don't need to plug it in. It doesn't create power, so there's no work, there's no Q. The flow velocities typically are not that big of a deal, okay? There's no elevation difference typically, okay? So actually, when modeling a valve, it's extremely simple. Typically, the only thing we need to be concerned with, H1 equals H2. The enthalpy before equals the enthalpy after for a valve. That's it. That's all you need to know with a valve, okay? So that's usually how we model a valve. Okay. It's basically just there to drop the pressure inside the flowing fluid. You might say, well, why would we ever want to drop the pressure inside of a flowing fluid? Okay. So. Yeah.
If you drop the pressure, would that mean that if we're doing say saturated water, wouldn't that H value actually change a little since the pressure is changing?
Not much. Yeah, I mean there could be things could change slightly. Yeah, the velocities could change slightly and things like that, but not much appreciably. No. Let me give you a good example here of why we have valves. Okay, there's other reasons we have valves, but this is probably the best example I could think of. And let's take a look at this here. A saturated liquid 134A is at 100 psi in a refrigerated cycle. It's throttled down to 10 psi. Now, when you see the word throttle, that basically just means there's a valve. Okay, now they didn't say that, but that's what it means. Okay, so it's just a valve that reduces its pressure from 100 psi to 10 psi. The A means absolute, right? Psi absolute. Okay. Determine the temperature at the exit of the valve. Okay. So how do we do this? Well, we only have one equation, H1 equals H2. So let's take a look at what do we know about state 1. State 1 is that, so it's sat liquid, and it's 100 psi. So we're in English units this time. So we got to go to our table, got to go all the way to refrigerant 134A for English units here. Here we go. All right, so we're 100 psi, okay? And we're at saturated liquid, right? So let's see here. That looks to me like my H is right there, 37.87. We'll just say that, 37.87. So my H1 is 37.87, and that's BTU per pound mass. By the way, let's just note here, what's the temperature? If you have a saturated liquid of refrigerant at that pressure, the temperature is right there, 79 degrees Fahrenheit. 79 degrees Fahrenheit. Okay, so let's, just for our own help here, let's write that down. 79, about 79 degrees Fahrenheit. Okay? Now, a throttle says that H1 equals H2, and that we also know about state 2 that the pressure of 2 is 10 psi. Okay? So now, let's go back to our tables, and we want to find out, we want to look at pressure table of 10 psi, and I want to know, does that H of 37.87 fit in the saturated region? Let's go here. PSI is 10, so that says that the enthalpy here, the low enthalpy is 30.156, and the high enthalpy is 98.68. So is my 37.87 between 3 and 98? Yes, right? Okay. That means that this is the appropriate table for me. That means I can automatically tell you what the temperature is of that fluid. Right there. Minus 29.52 degrees Fahrenheit. So this is an easy problem. It's minus 29.52 degrees Fahrenheit. What I've just shown you is very classic numbers approximately for what happens inside a standard refrigerator. Okay? If you feel the back of your refrigerator, it will feel fairly warm. Maybe even a little hot. I hope it doesn't burn you. I doubt it. But if you feel the back of your refrigerator and the coils that are in the back of your refrigerator, they are going to be warm because you probably have a saturated liquid at a higher pressure. Okay, it's definitely at a much higher pressure. Okay, and so it's warm. Okay, in the back of your refrigerator. Then, once the coils work all the way through the back of your refrigerator, what the point is it's trying to reject heat to your kitchen or wherever your refrigerator is, right? It's trying to put heat into your kitchen. Your refrigerator effectively heats up your kitchen, okay? And so it's going to put heat, and it's probably warmer than 97. You know, I don't know what it is, but it's probably higher, but not significantly higher. So it's probably a little higher than 79, but it's whatever. It's warm. And then what you have is a valve, okay? You've got a valve. This refrigerant flows through the back of your refrigerator, and then it hits the valve, and when the cycle starts, the valve is opened, and the pressure of that refrigerant drops greatly. When that happens, it gets real cold like that. When it gets real cold like that, you run it through your freezer. And you run it through your freezer, and it freezes whatever you want, right? And then when it warms up after it runs through your freezer, they put it through your refrigerator, and it runs through that. And then after it's done all its warming, then they compress it again, get a higher pressure, make it hot again, and put it back to your outside again. And that's the basic refrigeration cycle.
So
okay.
The entire temperature changes just that pressure drop.
Yeah, the pressure drop. Yeah, that's it. Yeah, yeah. That causes that refrigerant to get really, really cold, and that's what causes you to be able to cool inside your refrigerator.
You take some canned air and spray it upside down.
What's that?
Is that only with?
No, lots of substances do that. Lots of substances do that. Yeah, lots of substances. Yeah, refrigerants just do it better. That's all. Yeah.
Canned air and the computer
You could
testers.
do. Yeah, you can do it with air. Yeah, canned air. That's a very. Yeah, it will definitely cool off because it's air at a high pressure, and then you release it to a much lower pressure. It wants to cool, and so that's why it cools off. Yeah, same principle. Same principle.
If it's electric, so a liquid if you spray upside down.
Oh yeah, I believe it. Sure. Yeah. It's lots of things. It just so happens that refrigerants do it really well. Yeah. And so that's why we like them. Okay. And R134A does it really well. Not as good as ammonia, but ammonia is deadly. And not as good as refrigerant 12, but that hurts our ozone layer. So we'll go with this one. We're happy. And that's how that works. Okay. So throttling, which is just a valve, that's all it is very important. Very important to our lives. And it's easy. H1 equals H2. Anytime you see a valve, that's all you need to know.